Okay, we introduced logarithms. Okay, we said the log function could be rewritten as an exponential. I'm just going to jot that at the top of these notes as a reminder. We said that whatever, here's exponential form, and you can go back and forth between log form and exponential. And we said the base of the exponential is the base of the log. Okay, what the exponential equals is what you're taking the log of. Okay, and then the exponent in the exponential is what the log is set equal to. Okay, so this is the rearranging of those three parts that we learned about and practiced yesterday. So today we're going to talk about what a common log is and change of base formula. So I showed you in Desmos yesterday. Let me pull a Desmos back up here. Where to find the log button so you could check that you had rearranged it correctly. And I showed you on here, if you go to functions, down to the calculus section here, there was a log with no base, and then there was log where you could type a base. So yesterday we were using this, okay? But I told you we would talk more about this one that doesn't have a base written. It just takes you right into what you're taking the log of, okay? And that's what a common log is. When no base is written, okay, it is understood to be a base 10. A logarithm with a base 10 is called a common log, okay? So you can write it without a base. So log base 10 of x is the same thing as just log of x with no base written. Okay, so if you have no base written on your logarithm, it is a base 10, bless you, which we call a common log. Thank you. All right, so we are going to use what we talked about yesterday to evaluate these logarithms. Okay, so we can, if it helps you to write this as equal to x, and then rewriting it as an exponential, we can do that. Okay, so if we change this to exponential form, okay, I'll get my color coding down here again. Remember, the base of the log becomes the base of the exponential. If there is no base on that last one, what is that base understood to be? 10. Okay, so this is going to be a base 7. This is going to be a base 3. And this is going to be a base 10. Okay, and then we said it's raised to the power of whatever it's set equal to. In this case, that's what's missing. We don't know the power. We're asking ourselves to what power? Okay, and then it is going to equal what you were taking the log of. So we're asking ourselves 7 to what power is 49? Does anybody know it off the top of their head? Not 7 to the 7th power. 7 times 7 is 49, but what power would that be? 2. Okay, we're multiplying 7 twice by itself. 7 times 7 would be 7 squared. So x is 2. Now, if you don't know it immediately, or let me actually show you what we did before spring break in Unit 8. We did substitution here to get matching bases. Remember, we said if we can get the bases matching, which 49 can be replaced with 7 squared. And then we said if your bases match that 1-to-1 property, then the exponents must be equal. So x must equal 2. You don't have to write that last part out though. This line here, Most of you could do this in your head and say 7 to what power is 49? Oh, 7 squared, x is 2. Okay, but this just shows why it's 2. Because 49 is 7 squared. And if you've got 7 to the x equals 7 to the second, the x must be 2 for those to be equal. Does that make sense? Okay. Does anybody know 3 to what power is 27? 3 cubed. Okay, it's 3 times 9, but that's not what a power does. A power is multiplying it by itself. 3 times 3 times 3 is 27. So I can replace the 27 with 3 cubed, which shows me, oh, that x must be 3. Okay, 10 to what power is 100? Yeah, 2. 10 squared is 100. So if I replace the 100 with 10 squared, I've got my matching bases on both sides, so x is 2. So that is solving this algebraically by hand. Because if you just said in your head, what is log base 7 of 49? Y'all don't know that. You have to convert it to a form that you do know, which is exponential. Now, what tool do you have where you could do this a different way? Desmos. So if I have access to Desmos for this question, I could simply, as long as I know how to type this in, I could come and I could put, where is it? Log base 7 of 49. That's 2. That's what we got algebraically by changing it to an exponential as well. Everybody good with that? Okay. And then this one over here, for instance, didn't have a base. So you could literally just type log, or you could go use the log button without a base of 100. And there it is, 2. That's what we got. Okay, so you can check your answer. I would like you practicing doing this algebraically, because remember on our reviews and tests, some questions, yes, you can just use Desmos because it's just asking for a final answer. But sometimes you have those questions that are like, what would the first step be? Or what would the common base be? Like, we're testing that you actually know the process, not just can you put it in Desmos. So you do still need to understand how to convert this from log to exponential, even though you could just type that in. Okay, so you've got to know how to get that common base on the test. Okay, you need to make a note of that for yourself so you understand why aren't we just typing this in Desmos. Use Desmos to check your answers, but don't just do it in Desmos. You got to practice this so you'll be ready for the test. All right, so let's try it with 4. What is the base? What's the base on number 4? The base of the log? 12. So this is going to be 12, and then it's raised to this power x. That's our unknown. And it's going to equal what we're taking the log of, which in this case is 1. Now that one's tricky. 12 to a power equals 1. That's weird. Does anybody remember? It's a special exponent rule. Not a negative. It's not a negative or a positive. What's not negative or positive?
Wait, no.
No, fractions and decimals can be positive or negative. What's the only number that's not a positive or a negative? 0. Okay. What you need to remember here is your exponent rule. Okay, so I would make note of this and then star it. Okay. Anything, any base to the power of 0 is 1. Okay. So written out, the rule looks like this. We would say Okay, b can be anything. Anything to the 0 power is 1. Okay, so I know here, well, if I need to match the bases, if you were asked how to match the bases, you could rewrite this as 12 to the 0 instead of 1. So that means that x is 0. Does that make sense? Now that you remember that rule? As long as you know that rule, anything to the power of 0 is 1. That'll help you out. All right, what is the base in number 5? A 9. Okay, so I'm doing 9 to some power x, that's our unknown, is going to equal what we're taking the log of, which is 1 over 81. Now, here's where we get into what somebody mentioned a second ago. Is it a negative power? A negative power, a negative exponent, or negative exponent rule is what allows us to move terms within the fraction. Okay, so I can move this 81 up to the numerator by making it a negative exponent. Okay, right now, 81 is just to the 1 power. There's no exponent on it. So if I want to move it up to 81 instead of 1 over 81, I've got to put a negative 1 power on it. Then, how could I rewrite 81 as 9 to a power? 9 to what power is 81? Yeah, 9 squared. So I can replace the 81 with 9 squared. That negative 1 power is still there. And remember from last test, when you've got a power to a power, we multiply them. Guys, stop your side conversations, please. So this is 9 to the negative 2. So x is negative 2. I'll put a little couple notes out here. That one right there. Oops. I'm just going to rewrite the exponent rule as a refresher for you. You've got some base to the power of x. I guess I should put the negative there. Can be rewritten like this. So you can move the base value within the fraction if you change the power to negative. Okay, and then here, if you have a base to a power times another power, let's just call it c, you multiply x times c. Okay, so those are the rules that we just used there. So refreshing on our exponent rules. This exponent rule and this exponent rule. Can't forget about those. Okay, we refreshed on those back before spring break, but I know you had a little bit of time off to forget. Bless you. All right. So that's evaluating logs and understanding when there is no base, it's an understood base 10, okay, called a common log. Okay, so let's flip to the back. On the back is change of base formula. Okay, so some logs are not as easy to evaluate as the ones that we just did. Okay, and they require you to do a change of base formula. Okay, so evaluating or the change of base formula, what it is it's saying we can change any log base into a base 10. Okay, a log base b of a could be rewritten as a fraction where the numerator is the common log of a and the denominator is the common log of b. So we took that, what b was originally the base, it's not the base anymore. Now these are both base 10, and we're taking log of a over log of b. So you can rewrite any log to a common log using change of base. So if I do that, evaluate each log using change of base, okay, I would rewrite this as log of 54 over log of 2. How would I rewrite number 7? Log of what over log of what? Yeah, 136 over 4. Now, this does not mean, what I want you to understand, if you see a change of base formula used, or you see a log over a log like this, you do not get to cancel out the logs and say, oh, the logs go away, I'm just doing 136 divided by 4. That is not what is happening here. A log does not stand alone. This is not just log over log that you can cancel out. This is not log times 4. This is log of 4. Log of 136. So do not try to mark through and say, oh, logs go away and just divide. That is not how this math works, okay? The log and the 136 are together as a single term, okay? Log of 4 is one single term. You can't separate it like that. Is everybody good? How would I rewrite this last one? Good. 1 over 36 is the A value. What would be in the denominator? Log of 6. Good. Now, with the advancement of our technology and how we have Desmos and we're able to put in log bases, and TI calculators, the handheld graphing calculators have advanced, and they allow you to put in base values other than 10. Change of base formula is really not as pertinent as it used to be for calculating, because the calculators now will let you type in a base other than 10. Used to, you only had the option of typing in a common log. You couldn't do some other base, so you had to do change of base formula. But now that Desmos and graphing calculators let you type in any base, you really don't have to change this. Because if I want to type this in the way that it was given, log base 2 of 54, I have the option of doing that and calculating this. Okay. But if I didn't know how to put the base in, or before calculators were able to do that, you would have to do it with change of base and say log of 54 over log of 2. And you can see those are the same. Okay, so whether you type it in with the base value or as a common log using change of base, either one gets you the same answer. Does everybody understand that? So we'll go ahead and put these decimal answers. It does not say what to round to, so we're just gonna go, let's go 1,000. Here. Okay. So let's go with, that'll be 5.755, because the 8 will round the 4 up. Remember, this is tenths, hundredths, thousandths, and then you look one more to see if you round up or not. So 5.755. I'm going to put approximately. This is rounded. Okay, and then you can practice entering these other ones in the calculator. I'm just going to save us a little time and tell you approximately what it comes out to. Now this one comes out exactly to -2. You don't have to round that one. Feel okay about change of base and evaluating logs? Pretty straightforward, right? Okay, that's it for today's notes. I'm going to activate the practice in Delta Math for you to try this on your own. If you have not finished yesterday's for whatever reason, I would recommend you finish that first because it's due first.